For this worksheet, we're going to identify whether the carbon that is bonded to our heteroatom is primary, secondary, or tertiary. We will further classify some of these compounds as being allylic or benzylic. So we can also draw some carbocations and resonance forms, especially if they're allylic or benzylic. So for A, we're looking at this carbon here. So this carbon contains our heteroatom, and it is bonded to two other carbons. That makes this a secondary heteroatom, or a secondary alkyl halide, because this carbon bonded to the heteroatom is bonded to two other carbons. Now, one of those carbons is an sp2 carbon that is pi bonded somewhere else, or pi bonded to the next carbon. So that makes this specifically an allylic compound, or an allylic alkyl halide. So with spontaneous dissociation, what that means is, where would the carbocation be if the heteroatom just pops right off? And the answer is, well, right where the heteroatom is bonded. I mean, that's the initial place it's going to be. But because of this pi bond here and all of this electron density, what we're going to do is we're going to resonate. So this pi bond is going to come over and drop to satiate that positive bond, that positive charge, and form an additional resonance carbocation. So that becomes important as we start to react. For B, our heteroatom is out here, this OTS, and we'll talk about what that means later. But all you really need to do for this worksheet is notice that the carbon that it's bonded to is only bonded to one other carbon. That makes this a primary compound. For C, we're looking at this carbon. This is the carbon that contains the heteroatom, and it is bonded to two other carbons. That makes this a secondary compound, or a secondary alkyl halide, but one of those carbons is double bonded to another carbon. So specifically, this is an allylic alkyl halide. So what are the carbocations that may form? Well, initially, right here, right where the iodine was, so to speak. And then if that pi bond migrates in order to satiate that pi bond, then what happens is we form a tertiary carbocation. Tertiary carbocations are more stable, so you'll have to keep that in mind as well. For D, we're looking at this business as our heteroatom, and it is bonded to a carbon that is only bonded to one other carbon. So that makes this a primary compound. For E, we're looking at this carbon. This carbon contains the heteroatom. So how many carbons is that carbon bonded to? Well, we have 1, 2, 3. That makes this a tertiary compound. For F is a little difficult to see. This is supposed to be an I. It kind of runs into the bond, but this is supposed to be an I. So if you didn't catch that in your worksheet, that's what it's supposed to be. So as before, as up in these compounds, this is not only a secondary alkyl halide, this is allylic. And the carbocations that would form, well, initially it would be right where the iodine was, or that pi bond would come and satiate that charge in order to drop that carbocation here. Now, what we'll learn further, and I'm dropping this in as brain candy, this isn't something you need for this module, is one of these methyl groups could shift and migrate. So you could form all sorts of goodies with that particular compound. Now this compound G, we're looking at this carbon that contains the bromine, and this carbon is only bonded to one other carbon. That makes this a primary carbocation. This is not allylic, and it's not allylic because this carbon is bonded to an sp3 hybridized carbon. The allylic compound, or the allylic alkyl bromide, has an sp2 carbon bonded to it, and that sp2 carbon needs to be pi bonded to another carbon. So for H, here is my heteroatom. This is the carbon I'm going to analyze. So I have a carbon on one side and a carbon on the other. That makes this a secondary compound. It is not allylic and it is not benzylic because we don't have pi bonds. For I, This is the carbon we're going to analyze. So that with this particular carbon, we have 2 carbons attached to it. That makes this a secondary alkyl. Well, it's not an alkyl halide, it's not a halogen, but it makes a secondary compound. Now we have to analyze what is attached there. And because we have this sp2 hybridized carbon that has the pi bond to another carbon, that makes this an allylic carbon. So let's make those carbocations. Initially, we will remove the heteroatom, so that's where the carbocation will be. And then this pi bond will migrate in order to satiate that positive charge, and then we would get a positive out here. Now, a primary carbocation is not a stable carbocation, so it is unlikely that that will actually resonate and that it would react right here. This pi bond is too far away in order to resonate, so we're not going to consider that. For J, well, like F, it looks like the I kind of ran into the bond, but there is an iodine here. And we are analyzing this carbon, the carbon that attaches to the iodine. So we have 2 carbons attached to that, which makes this a secondary compound. And both of those carbons are sp3 hybridized. So that's it. We don't have anything else to say about that compound. For K, we're analyzing this carbon here because it is the one that contains the heteroatom. And this carbon is bonded to 2 other carbons. So this is a secondary compound, and specifically because the carbon that contains the heteroatom is bonded to a benzene ring. That's what this is, and when it's bonded like this, we call it a phenyl. This is called a benzylic secondary compound. So it's the carbon bonded to the ring that makes this benzylic. For L, we're looking at this carbon here, and we're going to analyze, and it's bonded to 2 other carbons. That makes this secondary. Oh, I didn't do the carbocation, but I'll do that in a minute. So we have a secondary compound here. Now, both of these carbons are sp2 hybridized, and they have double bonds bonded to other carbons, sp2 hybridized carbons. That makes this allylic, and we have more than one resonance structure. Not only can we form a carbocation between the 2 pi bonds like this, but we could migrate the pi bond over here so that we have our carbocation here, or we could migrate the pi bond over here so that the carbocation is over here. Now, I didn't do the carbocation for K. So initially, we're going to have this positive charge here. We're not going to migrate out of the aromatic ring. So this is going to be the only carbocation structure made from that benzylic group, or that benzylic carbon. So for M, we have our heteroatom here. We are analyzing this carbon. How many carbons is that bonded to? We have 1, 2, 3. So this is a tertiary compound. But it is a specific tertiary compound because the carbon is double bonded to another carbon. So this is an allylic, but it is tertiary. So let's make those cations. Initially, the cation will form exactly where that heteroatom was bonded. So that would be our first carbocation. Then the pi bond could come and satiate, which makes a carbocation here. Now, structurally, even though there would be resonance, they are the same compound. N, for N, this is where our heteroatom is, and that carbon is bonded to 2 other carbons, which makes this a secondary compound. Now, we do not have any pi bonds here, therefore it is just a secondary compound. Here we have our heteroatom out here on the end, so we're analyzing this carbon, and this carbon is only bonded to 1 other carbon. Now, this is a primary compound, but specifically because this is an sp2 carbon bonded to another sp2 carbon, that makes this allylic. And this one is fun because not only would we form this primary carbocation, which isn't necessarily a stable structure, But then we would resonate to move the carbocation here. And then this would come to satiate that. And then we would just walk down the chain. So we have 4 different carbocation structures for this primary allylic structure. And for P, we are analyzing this carbon. This is the carbon that contains the heteroatom. And we have 2 carbons bonded to this carbon. So this is not only a secondary, though, this is an allylic alkyl halide because we are bonded to an sp2 carbon that is double bonded to another sp2 carbon. So this is not benzylic because we have an sp3 carbon between our carbon of interest and the ring. So it's only allylic. So the first carbocation we would form is right here at the heteroatom, and the pi bond could come in and satiate that to move the carbocation or move the cation charge to the end. Now, a primary carbocation is not stable, so it is likely to not resonate and just stay right there.